Hi everyone, in this video we will discuss how to analyze the circuit. By analyzing a circuit, we can calculate the terminal currents and the terminal voltages of all elements. Consider a two-terminal element. Then we want to know two terminal currents and two terminal voltages. Since we have four unknown quantities, we have to identify four equations. Three equations are obvious. Sum of two terminal currents, I1 and I2, should be 0. A terminal voltage is equal to that of a connected node. Now we have identified three equations. One remaining equation is element specific. A voltage source, a current source, a resistor, a capacitor, and an inductor are representative two-terminal elements. Voltage, current sources specify the voltage difference and the current respectively. Ohm's law is applied to a resistor. A capacitor current is proportional to the time derivative of the voltage difference. The proportional coefficient is the capacitance C. A dual relation can be found in the inductor. Now we have four equations corresponding to the four unknown variables. However, unfortunately, we must know the node voltages because our terminal voltages are related with their connected node voltages respectively. Therefore, we need more equations whose number is the number of nodes. The basic principle of circuit analysis is Kirchhoff's current equal to the sum of currents flowing out of that node. In other words, once we fix the direction of a branch current, either incoming or outgoing, the sum of a branch current should vanish. Except for the ground node, we must apply the KCL to every node to analyze the circuit. Then, a natural question is its validity. Why do we have the KCL? It is revealed that the KCL is originated from the Maxwell equations. The total current density is a sum of the particle current density and the displacement current density. The particle current density is related with the motion of electrons and holes. On the other hand, the displacement current density is related with a time-varying electric field. According to the Maxwell equations, the divergence of the total current density should vanish. Now, we can integrate the divergence of the total current density. Since it is 0, the integral should be also 0. Applying the Gauss theorem, the volume integral can be converted into the surface integral. The surface integral can be separated into many pieces, and we can notice that the surface integral over a certain branch surface is the branch current for that branch. Finally, by combining the previous two relations, we can derive the KCL. As we have seen up to now, the derivation of the KCL is quite general. We have not introduced any assumption. It can be applied to an arbitrary number of branches. Also, it can be applied to time-varying situation. Since one node contributes one equation, we can solve the coupled set of equations to analyze the circuit. In the next video, simple examples will be shown. Thank you.